So yesterday we discussed OSI model in depth. Now we will discuss TCP header in depth, and we will discuss each and every field available in the TCP header and what is the meaning of that field and why it is important. Okay, so this is the layer 4 information. So the very first field is the source port. Okay, so you can see the minimum size of the TCP header is 60 bytes and the maximum size of the TCP header is the minimum is 20 bytes and the maximum is 60 bytes, right? So this is the minimum and it could be 20 bytes, and rest 40 bytes are optional data, so it could vary. So you would see in Wireshark that your TCP header length would be greater than or equal to 20, right? But it would be less than or equal to 60 bytes, correct? So your TCP segments are sent as internet datagrams, okay, and your TCP header will follow the IP header to deliver the specific information to the TCP protocol. Okay, so we will discuss each and every field now in detail, so that I'll give you the uh, brief description about the options available with us in the TCP protocol and what they are meant for. Okay, so let's start with the source port number. So you can see our TCP header will start with the source port number, and the size of that source port number is 2 bytes. Okay, so 2 bytes, which means 16 bits. Okay, so range of the source port would be 2 to the power 16. That is, your port number range will start from 0 and it will go till 65,535, because we are including 0. Okay, otherwise it would have been 65,536. Okay, so this source port number will contain the information about the source port which is sender is using, okay, for that application. It could be Chrome, it could be FTP, anything. So any random source port number which is sender is using while transmitting the information over network. Okay, then it will contain your, the very next field is destination port number, and it is also of 2 bytes, so same mathematics. So the range would be from 0 to 65,535, right? So this is very simple. So let me explain you one thing. So since this is a 32 bits long word, so one word is equals to 4 bytes. So this terminology is basically used for memory referencing, so your random access memory. So this is your RAM, and it comprises of the blocks, okay, memory blocks, and we put any put specific addresses to refer to these blocks. So whenever CPU is processing your information, right, so if the CPU requires any data to process, it will generate the logical address which will be referred to the physical address of the RAM and to get the information through the system buses and data buses, right? So here one word is equals to 4 byte, which means this is equivalent to one word, one word, one word, one word, one word, one word. So these words, if you club them, so these are 1, 2, 3, 4, 5 words. So 5 into how many bytes? 4 bytes. So your minimum header length would be 20 bytes. Okay, and what byte is equivalent to 8 bits, so you can write this information like this. Okay, now we will discuss sequence number. So the very next field in the TCP header is sequence number. So okay, so the next field is sequence number, and you can see that it is 4 bytes long. Okay, so this number is going to be very long. It's going to be 2 to the power 32, and which is going to be very long. Okay, so it represents the sequence number of the first data octet in this segment if SYN is not present. Okay, on the other hand, if SYN is present, the sequence number is the initial sequence number, that is ISN. Okay, and the first data octet is ISN plus 1. Right, don't be confused by these terminologies. I'm going to explain everything in Bashak, so don't get confused here. So the next field is acknowledgement number. Again, it is also 4 bytes long. Okay, so it is also going to be very large number. So if the ACK control bit which is present here, okay, if the ACK control bit is set, then this field contains the value of the next sequence number the sender of the segment is expecting to receive, right? And once the connection is established, this is always sent. So I know this is a bit confusing right now, so let me go to the Wireshark and let me explain you what do we understand by the sequence number and the acknowledgement number. Okay, so let's look here. So this is your first packet and it is a SYN packet. Okay, so this is the client machine which is 190, it is starting from 192, and this is the destination machine which is starting from 172. Right, so the client is trying to establish the TCP connection, so it is initiating the TCP connection request by sending SYN packet, right? So you would see that sequence number for SYN packet is 24472944724. Right, so this is a random number which the system has generated. Since it is a 32-bit long number, so the value is going to be long, right? And now you can see the next sequence number field, it is the exact same value, because the length of the packet, since it is not carrying any data, it's a normal SYN packet, there is no data field present till now, because we are in a phase of initiating connection and we are in a phase of establishing TCP connection. So the next sequence field is going to be same. Okay, and since we are initiating the TCP request, so initially we will acknowledge 0. Okay, we haven't received anything from server, right? So now this is the server and it is acknowledging back to the client by sending SYN ACK. So what server is doing, server is sending two packets, one is SYN and one is acknowledgement. So they are combined together and they are known as SYN ACK. That's why the entire process is known as TCP three-way handshake. Correct. So now server is telling the client that this is my sequence number. Okay, this is the random sequence number which is server is owning. So it is telling that this is my sequence number and my next sequence number would be this. It will be also same because the length of the packet is 0. They are not carrying any data, right? And it is giving acknowledgement to the sequence number which it has received from the server. So it is telling that I have received till 724. So this was the sequence number uh, of the client. So the server is telling that I have received till 724. Now you need to send me the next packet from 725, because you can see here the next sequence number is still 724. Since there is no data present, so it is not incrementing. So server will tell the client that you need to send your next packet with this sequence number 725. You need to increment the value by 1. Okay, so this is an interview question as well, when the interviewer will ask you that why these SYN packets, in the TCP three-way handshake, the sequence number is incremented by 1, but when the actual data transfer happens, so it is incremented by the data bits. So this is the explanation for that, right? So in the third packet, which is the acknowledgement packet being sent from the client itself, so client will say, okay, so my sequence number is now 725. Okay, and my next sequence number will always remain 725 since I'm not sending any data bytes, so length is still 0. Okay, and I'm giving you the acknowledgement number that I have received your SYN plus ACK. So I'm giving that I have received 4 5. I mean the I am expecting the next packet to be start from 454. Okay, so you can see the SYNAC sequence number was 453. Since the fields are still same, the next sequence number is still same. That's why client is also incrementing the value by 1, so that it is also telling server to send your next packet starting from 454. Since we are not exchanging any data, it is not adding any value to our sequence number. To establish a sequence between the segments, we need to increment the value. Okay, so you can see now the for SSL handshake, still your client will send the uh, data and it's a client hello. Okay, so client will initiate the SSL handshake as well. So you can see now the sequence number is 725. So sequence number for acknowledgement is also 725, and sequence number for client hello is also 725, because client is sending the data, not server is sending the data right now. So client has sent these two packets together. One is the acknowledgement and another one is the client hello. Okay, so that's why your sequence number is 725. And now you can see the next sequence number is 912. Okay, so if you are going to add 187 to this number, so the result will be this 912. Okay, you can do the mathematics. And again it is giving the same acknowledgement that I have received 454. I mean, you need to send your next packet starting from 454. Okay, so now your server is giving the acknowledgement, and now you can see the sequence number is 454. Okay, and the next sequence number is still 454 because length of the packet is 0. Since this is the acknowledgement packet, so length would be 0, and it is giving you the acknowledgement this yes, I have received till 912. So if you go back here, so the next sequence would be 912. So now it is not incrementing the value by 1, you can see here. So it will only increment the value by 1 whenever there is no data present in the packet, whether it is a SYN packet, acknowledgement packet, SYNAC packet, something like that. Okay, so it will increment the value and it will say now you need to send the next sequence number by incrementing by 1. Okay, so so the next packet is server hello. So you can see the sequence number is still 454. Now the sequence number has changed to 884 because the server hello contains data of length 1430. If you add this number here, you can see that it is, the result will be this. And again, it is acknowledging to the same number, that is 912. I hope this has explained you in detail about the sequence number and the acknowledgement number. In my coming videos, I'm going to explain the TCP three-way handshake and SSL handshake in depth. So we will cover, your doubts later on. Okay, so the next field is data offset, right? So as you can see on the screen, it is only 4 bits long. So let me tell you what is data offset. So yeah, so data offset, this indicates from where your data will begin. Okay, in short, it is telling you that TCP header will end after certain bytes and your actual data octet will start. So let's say if your header TCP header, let me select the marker. So it says if your TCP header length is 32 bytes. So this data offset will tell you that after 32 bytes, after processing 32 bytes, your actual data octet will start. Okay, so this is what this data offset field tells you about. Now the next field is reserve bits. So these are the 3 bits which are reserved for future reference. They are always set to 000. Then we have control flags. Okay, so there are 9 control flags which has been introduced in the TCP. Earlier there were 6 flags only and 6 reserve 6 reserve bits. So we have taken 3 more bits out of the reserve. Now there are 9 control flags. So we will discuss each flag through Wireshark. Okay, so one flag is 1 bit equivalent. Okay, so let's come here and let me open up this flag section here. So you can see the reserved, these are 3 bits not set. Then we have none's flag, it is also not set. Then next we have congestion window reduced flag. It will tell you whether your congestion, your congestion in the uh, network has been reduced or not. So it is for the congestion purpose. Then we have ECN echo. This is also for the congestion purpose and it is also not set. Then we have urgent flag. Then we have acknowledgement. Okay, then we have push, reset, syn, fin. Okay, so I'll cover each of these flags in later in coming video. Okay, so right now I'll not cover each and every flag here, but I'll discuss them later on. Right, so let's go back to the TCP header again. So the next field after control flags we have window size. Okay, so you can see it is also 2 bytes long, right? So it is also 2 bytes long. So what does that mean? What do you mean by window size? So it represents the data. It represents the number of data octets beginning with the one indicated in the acknowledgement field while which the sender of this segment is willing to accept. So I know it's hard to understand, so I'll repeat this statement again. So it represents the number of data octets beginning with the one indicated in the acknowledgement field which the sender of this segment is willing to accept. Okay, so sender will tell the client will tell the server that I can accept only this much amount of data, don't send me more than this. Okay, similarly server will tell that I can handle this amount of data, don't send me more than that, right? Okay, so the next field is checksum, right? It is also a 2 byte long field. Okay, so the checksum field is the 16-bit ones complement of the ones complement sum of all 16-bit words in the header and text, right? If a segment contains an odd number of header and text octets to be checksummed, then the last octet is padded on the right with zeros to form a 16-bit word for checksum purposes. I know that that was a complement, complex statement. Let me explain you this. So if your header octets and text octets are odd in number, so we need to add some padding bits to form a 16-bit word. That is your 2 byte information. As simple as that. Okay, so next, now move on to the urgent pointer field. So this field is also 2 bytes long. So this field communicates the current value of the urgent pointer as a positive offset from the sequence number in this segment, right? So the urgent pointer points to the sequence number of the octet following the urgent data. This field is only be interpreted in segments with the urgent control bit at set. So what does that mean? So if your control bit, your urgent flag is set, right? If your urgent flag is set, then only your urgent pointer will be interpreted and it will point out to the data octet from where your urgent data is starting. Okay guys, so the now we will discuss control bits. Okay, so there are 9 control bits which I was telling you earlier as well. So let me write all of them here. So your first is nonce, second is CWR, third is ECN echo, then we have urgent point flag, then we have acknowledgement, then we have push, then reset, syn, and fin flag. So these are the this is fin. So these are the 9 flags which are used to control the data transmission. Okay, so you can see 9 flags. So now what do you understand by nonce, So a random 1-bit value is encoded in the two ECT code points. So ECT stands for ECN capable transport. So a random value is taken which is being encoded into two ECT code points in the ECN field of the IP header. The 1-bit sum of these nonce is returned in a TCP header flag. Okay, so there are two code points in the IP header which is a random 1-bit value. Okay, so we take sum of those 2 points and the result is stored in the nonce field. Okay, so the next flag is CWR. It is a congestion window reduced, right? So CWR flag is set by the sending host to indicate that it received a TCP segment with the ECE flag set and had responded in congestion control mechanism. Okay, so ECN stands for explicit congestion notification. So if there is a congestion in your network, so this is the mechanism to detect the congestion and inform the sender and receiver, I mean your client and server, to reduce the data transmission window so that they can get the information without over congesting the network, right? So the next flag is ECN echo. So ECN stands for explicit congestion notification. So it is used to echo back the congestion indication, that is, signal the sender to reduce the amount of information it sends. It then acknowledges this congestion indication by sending a segment with the CWR bit set. Okay, so basically you can refer that these three fields are used to detect the congestion in your network. Okay, and to implement the congestion control mechanism. So the urgent flag, it is used to to point out the CPU that there is some urgent information, I mean there is some urgent data which you need to process. Okay, so if this bit is set to 1, then CPU will interpret this field. Okay, so if this bit is not set, then CPU will not interpret this field. It will leave it like this. But if it is set, it will go back here, it will check this urgent pointer and it will see where this urgent pointer is pointing, which means that data is critical and that needs to be processed first. Okay, then there is acknowledgement flag. So it is basically telling you that I have received this amount of data, and it is just to give you acknowledgement of that. So if it is set, so it is this significant field significant for acknowledgement number, right? Then we have push. So push flag is basically a push function, which means if this is set to 1, it means whatever information you're receiving, send it right away. Don't wait for window to get full. Okay, so whatever information you have received, and after that, if the push flag is set to 1, then send it right away. Okay, so reset, and then we have reset flag. So reset flag is used to reset the TCP connection. Okay, then we have syn flag, and it is used to synchronize the sequence numbers. Then we have fin flag, so it is sent by the sender that no more data will be required, or I'm not going to send any more data. So it is basically indication to close the TCP connection. Okay, so guys, we will discuss optional data field in the next lecture. Okay, so in this video I have used certain new terminologies which can confuse you, but don't worry, you can refer to RFC 793 for that. Okay, and I would request you to listen to this video again and again so that you can get the basic understanding of TCP header.